So, we were discussing about thermodynamic relationships, and today we will continue with very interesting thermodynamic relationships concerning internal energy, enthalpy and specific heats at constant pressure and volume. So, we will start with the internal energy. So, you can write the internal energy as a function of two independent intensive thermodynamic properties, U as a function of T and V. So, du is this one. So, this is the rule of partial total derivative is the sum of the partial derivatives. So, this is one expression U as a function of T and V. Okay. Now, let us use the TdS relationship Why we use this TdS relationship? Because this also gives you U as a function of not T and V, but U as a function of S and du as a function of ds and dv, but you can write now S as a function of T and V. If you do that, you can have an expression from here which can be compared with this form. So, with that motivation we will write S as a function of T and V. So, ds So, then we will substitute that ds here. So, let us write T okay. Then del S del V at constant temperature, this one of the thermodynamic relationships will give you the corresponding in terms of the measurable parameters. See this third Maxwell's equation, that from here we can write this is del P del T at constant V from this star which is written on this part of the board. Following that we can write du, so this is dt, right. So, du is equal to T del S del T at constant V dt plus T del P del T at constant V minus P dV, right. So, now compare this equation with this equation, they are essentially the same. before comparing, this is by definition nothing but CV, right. So, by comparing these two, the first observation that you have, T del S del T at constant V is CV, and similarly T del P del U del T at constant, sorry, del U del V at constant temperature is T del P del T at constant volume minus P. Okay. So, to summarize, you can write du is equal to, from this equation, CV dt plus dV, not dP. So, this is an expression. Now, for an ideal gas, you have PV is equal to RT. So, del P del T at constant volume is equal to R by V, right. So, T del P del T at constant volume is RT by P, that V, that is P. So, this part becomes 0, P minus P. So, then du is CV dt for an ideal gas. This we prove by this derivation, which we assumed earlier, that du equal to CV dt for an ideal gas. This we now prove here. Now, does it? So, this is for an ideal gas. Now, is it sufficient to tell that U for an ideal gas is a function of temperature only? Not really sufficient, because you also have to establish that CV is a function of temperature only for an ideal gas. So, that we will see as another step, but before that we will consider enthalpy instead of internal energy and do a similar exercise. I will just follow exactly the similar steps. So, just so that you can follow it nicely. So, enthalpy. So, enthalpy we will write H as a function of T and P. Okay. So, dH will be del H del T at constant pressure. Why we use it as why we write enthalpy as a function of T and P? Because we will use the TdS equal to dH minus VdP. That is why this P dependence we could also write it as a function of T and V, but that will not serve the mathematical manipulation purpose. Fundamentally it will not be wrong, but it will not serve the mathematical derivation purpose. So, this is not CV anymore. Next we will write TdS is equal to dH minus VdP, and this S as a function of T and P. So, ds okay. So then we will use one of the Maxwell's relations here, del S del P at constant temperature. Let us find out, it is the last Maxwell's equation, del S del P at constant temperature is minus del V del T at constant pressure. So T into del S del T at constant pressure, so we substitute, we make it here with substitution, into dt plus or so minus T del V del T at constant pressure into this is T dP, sorry, this is dP is equal to dH minus VdP. So dH is equal to T del S del T at constant pressure dt plus V minus T del V del T at constant pressure into dP. This by definition is Cp. So if you compare these two, this is Cp. So you are left with dH is equal to Cp dt plus V minus so this is the pressure dependence of enthalpy, this is the temperature dependence of enthalpy, very similar to the internal energy expression. These kind of expressions are very useful because if you know the equation of state, pressure, volume, temperature relationship, you can easily calculate these partial derivatives and get an expression for H by integrating this, right. So again we consider an example, ideal gas. So ideal gas PV is equal to RT, so del V del T at constant pressure is equal to R by P. So T del V del T at constant pressure is equal to RT by P, that is V. So V minus that becomes 0, so that means dH is equal to Cp dt. So for ideal gas dH equal to Cp dt and du equal to Cv dt, these two things we have derived, but we have more general expressions. Even if it is not ideal gas, but you give an equation of state, you can find out the change in enthalpy and change in internal energy. These two are very important things. Why out of all those things we have done all this? Because to calculate the heat transfer, work done etc. using the first law of thermodynamics, for a closed system you require change in internal energy and for a flow process you require change in enthalpy. So that is why the dH and du, these expressions are very important, which can be used fundamentally in conjunction with the first law of thermodynamics. So we have considered internal energy and enthalpy. Now we will consider the expressions for Cp and Cv. In particular, it is the expression for Cp minus Cv that is important, because Cp Cv we have the expressions as they are. So our objective now is to find out Cp minus Cv. Okay. So to do that, because the entropic derivative can be written in terms of Cp and Cv if S is expressed as a function of temperature, pressure, volume etc., So, we will start with S as a function of T and V. So, ds right. So, just now we have done a derivation which tells that this is equal to Cv by T, because T ds T del S del T at constant volume is Cv for the internal energy derivation, just now we have done it, and this one from one of the Maxwell's relationships, this star marked Maxwell relationship, this is del P del T at constant volume. So, we are expressing the non measurable in terms of measurable. This TdS relationship is very important, this Maxwell relationship is very important, in fact all these are important, because right hand side there are non measurable parameters, left hand side you have pressure, volume, temperature which are measurable parameters. So, then we have S as a function of T and P. So, ds this just now we have derived is Cp by T. And this one from one of the Maxwell's relationships, del S del P at the last one at constant temperature is minus del V del T at constant pressure. Now, this is ds, this is also ds, so they can be equated. So, if you equate these two, you have Cp by T minus del V del T at constant pressure dP is equal to Cv by T minus this is Cp by T dt, Cp dt by Cp by T dt, Cp by T dt minus del V del P at constant pressure dP is equal to Cv by T dt plus del P del T at constant volume dV. So, Cp minus Cv by T dt is equal to del P del T at constant volume dV plus del V del T at constant pressure dP. Okay. Now, see this has a form of T as a function of V and P, right, dt expressed in terms of dV and dP. So, if you write T as a function of V and P, then dt right. So, now you can compare this 1 and 2. if you compare 1 and 2, then you have Cp minus Cv by T okay. So, the ratio of these two coefficients is same as ratio of these two coefficients, right. Then, so this is nothing but del P del T at constant volume into del V del T at constant pressure, right, because 1 by del T del V is del V del T. Now, we can so this is an expression for Cp minus Cv, but we want to get a little bit more simplification. So, we can use this chain rule del P del T at constant V into del T del V at constant P into del V del P at constant T is equal to minus 1, right. So, if we do that, then del P del T at constant V, this one is equal to minus 1 divided by del T del V at constant pressure into del V del P at constant temperature. And this is nothing but minus del V del T at constant pressure into del P del V at constant temperature, right, just inverse. So, Cp minus Cv, the final expression is minus T del V del T whole square, right, at constant pressure into del P del V at constant temperature. Okay. So, with this equation, so this is a very important equation because this does not depend on which fluid, I mean what is the constitutive or what is the equation of state. Now, one thing we can conclude that irrespective of the equation of state, this will be negative, right. If you increase the pressure, the volume should decrease, right. So, del P del V at constant temperature is negative, T is absolute temperature which is positive, and this is a square term. So, this is positive. So, minus minus plus makes the entire thing positive. So, that means the first observation is that Cp minus Cv is greater than 0, that is Cp is greater than Cv. This is first observation. Second observation is that for incompressible substance, there is no change in volume, that means the right hand side is 0. So, Cp is identically equal to Cv, not approximately, identically equal to Cv. There is another case when Cp is identically equal to Cv, but the substance is not perfectly incompressible. Can you give an example? So, I am repeating my question. One case perfectly incompressible, you can understand that perhaps no fluid is perfectly incompressible typically if it is in liquid or gas state. Solid almost perfectly incompressible, but liquid and gas state will have some compressibility, liquid less, gas more, but still some compressibility. So, can you give an example when Cp is perfectly equal to Cv, although it is not a perfectly incompressible scenario. Consider water at 4 degree centigrade. So, water at 4 degree centigrade will have maximum density, right. So, because it has maximum density, its specific volume versus temperature derivative, this is a representative of density 1 by density. So, this will be 0 for water at 4 degree centigrade, that means Cp is equal to Cv exactly, right. This is a very interesting situation where incompressibility is not exact, but Cp minus Cv equal to 0 is exact. And the final observation that we consider is ideal gas. Ideal gas, you have PV equal to RT. So, that means you have and del P del V at constant temperature is, so P is equal to RT by V square, RT by V. So, del P del V at constant temperature is minus RT by V square, right. So, this is so Cp minus Cv is equal to minus T into the square of this, that is R square by V square into minus RT by V square, right. So, now you use the equation of state. So, P square V square is equal to R square T square, right. So, V square is equal to R square T square by P square. So, this R square and this R square cancels. So, then you can also use T is equal to PV by R. So, if we change everything to okay. So, you can cancel these ones, hopefully all these, yes.
I think del V del T at a constant pressure is R by P, just check once.
So, del V del T at constant pressure is R by P, sorry that is why this is. So, I will redo it, there was an algebraic thing. So, Cp minus Cv, so this is R by P not R by V, right, del V del T at constant pressure is R by P, right. So, Cp minus Cv will be minus T into del V del T at constant pressure square R square by P square not V square, last time we wrote V square, into this one minus RT by V square. Okay. So, now P square V square is R square T square, right. So, you can write this as minus T R square into minus RT P square V square is R square T square. So, you get r square cancelled, t square gets cancelled with this t square. So, this becomes r. So, this proves that Cp minus Cv is equal to r for an ideal gas. This does not assume constant Cp and Cv. Okay. So, we can derive from these thermodynamic relationships certain very useful expressions for internal energy, enthalpy and differences in the specific heats. We can derive many more relationships, it is just a mathematical manipulation of partial derivatives, but these relationships are very useful for conceptually deriving some unknown properties or derivatives of unknown properties in terms of derivatives of measurable or known properties. With this we conclude this lecture and we will start with a different topic in the next lecture. Thank you very much.